All right, so now we're going to look at the subject of rigid body motions. Okay. All right, so up to now, we focused on mobility, degrees of freedom, okay, the idea of a configuration space, and also how to, right, keep an object from moving, okay, with these contacts. Okay, the idea of force closure and form closure. Okay, now we're going to let the object move freely in space. Okay, so remembering that a robot is nothing more than just a bunch of bodies connected by joints. Okay, we have to find ways to describe the position and orientation of a rigid body. Okay, we talked about that a little bit. We're going to do that in a more formal and thorough way here. Okay, so really we're going to focus on the description of the configuration of rigid bodies. Rigid bodies in space. Okay. And we're going to do this in a systematic way. Okay. So here's a way to do it. Here's a rigid body in space. Okay. What we're going to do is we're going to describe things in terms of reference frames. Okay. So first we need a frame that's fixed to ground. Okay, and we're going to be drawing a lot of these pictures from now on. Okay, so I want to get some notation down. So I'm going to call this the fixed frame. So this is going to be the fixed frame. Sometimes I'll call it the space frame. Okay. And to remind you that it's fixed to ground, we're going to use this type of checking notation here. Okay, and I'm going to label this reference frame S. Okay, to denote the space frame or the fixed frame. Okay, now I'm going to attach another reference frame, this time to the rigid body. Okay, and this frame moves with the body. Okay, it's rigidly attached to the body. So if the body moves, the frame also moves. Okay, so this frame I'm going to call the body, the moving frame, because it moves with the body, and also sometimes call it the body frame. Okay, and I'm going to use the notation B in these parentheses. Okay, all right. So I want to be able to describe the position and orientation of this body. Okay, so the natural way to do it is to describe the position and orientation of the B frame using the S frame coordinates. Okay. Okay, so here's one way to do it. We draw a vector like that. Okay, let's call this vector P, arrow. Okay, and I'm going to also, this time, I'm going to label the axes of the fixed frame using large X, Y, and Z. Okay, so this is large X, X hat, large Y hat, and this is large Z hat. Okay, and I'm going to do the same for the unit axes of the body frame. So let me call this small X hat, small Y hat, and small Z hat. Okay, all right. Okay, so I want to describe the position and orientation. the position seems pretty easy, right? So position, the vector p, okay, is all we need. So vector p, if we use the fixed frame coordinates, okay, it's going to be the form p1 times p1 in the large x direction plus p2 in the large y direction plus p3 in the large z direction. Okay? Okay, so we can write the column vector p in the form p1, p2, p3. Okay, and this takes care of the position. Okay. Okay, now let's think about the orientation. Okay, so how are we going to describe the orientation? Here's an idea. Why don't we write down the directions of the small x, small y, and small z vectors, okay, using our fixed frame coordinates. Okay, so let's do that. So orientation. Okay, so it's kind of a brute force method. So small x hat, okay, it's going to be of the form, say, r11 times large x plus r21 large y plus r31 large z. Okay, and we can do similar. We can write down similar expressions for y hat and z hat. Y hat r12 x plus r22 y plus r32 z, and then z hat is r13 r23 y hat plus r33 z hat. Okay? Okay, so 9 numbers. So let's organize these 9 numbers into a 3x3 matrix. R11, okay. All right, so there it is. So I'm going to use these 9 numbers to describe the orientation. Okay, so we have, let's see, 3 numbers for the position, 9 numbers for the orientation. 9 plus 3, 12. That seems a lot, right? Seems too much. All right, how many do we need? What's the minimum number we need to describe the position and orientation? Okay, we need 6, right? 12 parameters. Okay, so this is 6 too many. Okay. So let's see, where are the redundancies coming in? Okay, so we have to think about the constraints. Okay, and constraints are that what? Well, these vectors, x hat, y hat, z hat, these are unit vectors. Okay, unit vectors. So that means their length is 1. Okay, and they're also orthogonal, right? X and y are orthogonal, y and z are orthogonal, x and z are orthogonal. Okay, so if we impose those constraints on these 9 numbers, we get some conditions, right? Okay, so first constraint is norm x, norm y, okay, norm z. Okay, these are all equal to 1. Okay, so if we write down those constraints, you know what it's going to be, right? R11 squared plus R12 squared plus, R21 squared plus R31 squared equals 1. Okay, and two more. That constraint. And we also have the constraint that x hat and y hat are orthogonal to each other. So we can write it this way. X hat dot y hat is equal to 0, okay, which can be written R11 times R12 plus R21, R22 plus R31, R32 equals 0. Okay, and we have two more, right? Y dot z equals 0, okay? And we also have the final constraint x dot z equals 0. Okay, and then we have x hat dot z hat equals 0. So we have these constraints. Okay, so we have 6 constraints. 1, 2, 3, 4, 5, 6. Okay, so 9 parameters, 6 constraints, 9 unknown, 6 equations, 9 minus 6, 3. So 3 independent parameters. Okay, so 3 plus 3, 6. Okay, so that works. Okay, so we have these conditions on R. Is there any other condition that we're missing? Okay, let's think hard. Is there something that we're missing? Okay, he says there's a notation. I screwed up some notation here. Seems okay to me. I think it's okay. 1, 1, 2, 1, 3, 1. Yeah, I think it's okay. Okay. Okay, so we have 6 constraints. Okay. Now, there is one constraint that we haven't talked about, okay? Okay, and that's the constraint of this issue of right-handed versus left-handed frame. Okay? Okay, this is right-handed. Okay? Now, what does it mean by right-handed? Okay, and speaking as a left-hander, okay, a right-handed frame here implies that x hat, if I take the cross product of x and y, this is going to be z hat. Okay? So now, what's a left-handed frame? Here's x, y, z. That's my right-handed frame. So a left-handed frame now has z pointing in the other direction. Okay, so this is left-handed. Okay. All right, so is one better than the other? Well, not really, but you know, we live in a right-handed world. Okay, it's not my choice, but we live in a right-handed world. Okay, so we use right-handed frames. Okay, so we haven't taken care of this constraint, this right-handed constraint. It's not reflected in the 6 equations above. Okay, so let's go over here where we have more room. Okay, so let's see, what are the conditions imposed on the R's? Okay, well, I want to remind you of a result. Okay, if I have a 3 by 3 matrix, okay, if M is 3 by 3, okay, and I label the columns of M, say, A, B, C. Okay, so these are my columns, A, B, and C. Okay, three-dimensional column vectors. Okay, then there's a convenient formula for calculating the determinant of M. Okay, and that is to take A transpose times B cross C. Okay, so what I can do now is I can use this formula and apply it to my R. Okay, so apply this to my rotation, my R, which is R11, R21, R31, R12, R22, 2. Okay, and R13, R23, R33. Okay, and remember that, note that this first column corresponds to X hat. Okay, the second column corresponds to Y hat. Third column corresponds to Z hat. Okay, so if we apply this determinant formula to this, what we're imposing is that for a right-handed frame, X cross Y equals Z. Okay. So the determinant of R, Y cross Z in a right-handed frame should be X. Okay, so X transpose X, 2 unit vectors, is 1. So the determinant of R has to be plus 1. Okay, for a right-handed frame. For right-handed frame. Okay, what about for left-handed frames? For left-handed frames, determine R equals minus 1 for left-handed frames. Okay, all right. Okay, so the constraints that I described to you now can actually be expressed in a very nice compact way. Okay, so the constraints can be expressed as the following. R transpose times R equals I. Okay, so this takes care of the requirement that all the unit vectors are unit length and the unit vectors are orthogonal to each other. Okay, that takes care of that. Now the right-handed frame constraint, I've already written it down. Determinant of R is equal to plus 1. Okay. All right, so we have 9 numbers, okay, contained in R, 6 constraints here. This looks like a 7th constraint, okay, but this 7th constraint doesn't do anything in terms of affecting the number of independent parameters. Okay, so here's the situation. So if we have, say, let's say this is R9, 9-dimensional space. Okay, then R transpose R equals I, 6 equations. Okay, 9-dimensional space, 6 equations. What do we get? We get a 3-dimensional surface, right, inside here. But this 3-dimensional surface looks like, okay, so here's one, here's another. Okay, so these two are obtained from R such that R transpose R equals identity. So we get these two three-dimensional surfaces that are not connected to each other. They're disconnected. Okay? So this part, determinant of R happens to be plus 1. This part, determinant of R, happens to be minus 1. Okay? Okay, so this determinant R is plus 1. This condition just throws this away. Okay? So we're still left with one three-dimensional sort of a surface, if you will. Okay? All right. So we're going to give this a name. Okay? We're going to call it SO3. Okay? And S stands for special. O stands for orthogonal. Okay. SO3, okay, is defined to be a set of 3 by 3 real matrices, okay, that satisfy condition R transpose R is the identity, okay, and the determinant of R is plus 1. Okay, so it's SO3. It's also called the rotation group. Okay. Or sometimes we'll just refer to it as orientations. Okay. Okay, so from now on, we're going to describe orientations in terms of these rotation matrices. Okay, so your first reaction might be, wait, I thought we had this long discussion that 9 numbers is too many. Okay, we only need 3. Why are we using this? Well, we're going to, eventually look at 3-dimensional representations for R. Okay, but for now, I want to look at some basic properties of these rotation matrices because it turns out they'll be quite useful when in describing rigid body orientations. Okay, so let's spend the next 10 minutes or so going over the basic properties of rotation matrices. Okay, so properties of SO3. Okay. All right. So this is, in some sense, it might be a little bit of a review of linear algebra for you. Okay. At least it will serve to remind you of some important linear algebraic, results, facts that we'll be using throughout the course. Okay. So the first is suppose I want to take the inverse of R. What is it? Well, in the case of a rotation matrix, it's quite easy. It's just the transpose. Okay. Now, why? Well, the definition of of an inverse is if I multiply some matrix by another matrix and I get the identity, then these are inverses of each other. Okay? So this is, since from the definition R transpose R equals I, okay, R transpose has to be R inverse. Okay? And this is a square matrix. So it follows immediately from the definition. Okay, second property. If I multiply 2 rotation matrices together, what do I get? Okay, so if R1, R2 are rotation matrices, okay, then it turns out that the product is also a rotation matrix. then R1 times R2 is also an SO3 matrix. Okay, so this is kind of a remarkable fact. I mean, if you multiply two matrices, in the general case, you lose any structure. But if these two matrices happen to be rotations, you can multiply them, always get rotations. Okay? All right, so this is pretty easy to show. Just have to apply the definition. So R1, R2, transpose R1, R2. What should this be? This should be the identity if this is supposed to be a rotation matrix. Okay, and it's simple enough. R2. And remember, when you transpose a product of two matrices, remember the order switches. Okay, R2 transpose R1 transpose R1 R2, right? R1 transpose R1 is by definition the identity. R2 transpose R2, also the identity. Okay, so that checks out. Okay, we have one more thing to check. The determinant of R1, R2, this should be what? +1, right? But now if you remember the properties of determinants, it's determinant R1 times determinant of R2. R1 is a rotation, so this is +1. R2 is a rotation, this is also +1. The result is +1. So everything checks out. Okay. Good. So the product of two rotations is also a rotation. Let's see. So we have the inverse property. It's closed. Okay. So here's another property. So if X is a three-dimensional vector, okay, and I multiply X by some rotation matrix R, okay, so if I take R times X, okay, that's going to be another three-dimensional vector, and I take its length, okay, this is also going to be the same as the length of X. Okay, again, this is quite easy. Take the length. Let's take the length squared. Okay, so this is going to be X transpose Rx, which is just X transpose X, which happens to be just the norm of X squared. Okay, so there we go. Very straightforward calculation. Okay. There are a few more properties on rotation matrices, especially concerning the eigenvalues and eigenvectors, but we're going to look at those later. Okay. Today I want to conclude with one property that sort of gives you a direct connection with this frame interpretation. Okay. Okay. So the following. Okay, property provides a physical sort of interpretation all right, so what we're going to do is we're going to draw three reference frames. Okay, so here's frame 1, frame A. Here is frame B, and here is frame C. Okay, three reference frames, all in different arbitrary orientations. Let me label the unit vectors XA, YA, and ZA. Same thing for B, XB, YB, ZB, XC, YC, ZC. Okay, so XB, YB, ZB, XC, YC, ZC. Okay? Okay. Let me describe xb using frame A coordinates. Okay, so it's going to be something. Maybe R11 xa plus R21 ya plus R31 za. Okay, yb. Okay, also going to be something in terms of xa, ya, and za. R12 xa plus R22 ya plus R32 za. Okay, and so on. Okay, I'm not going to write that line. Okay, I can do this, right? Okay. Okay, I can rearrange those three lines into this form. Okay, this times okay, I can write it this way. If you don't believe me, try it. You can take my word for it. Okay, so this is true. Well, if I play this game, okay, this time write C in terms of B. Okay, I can do something like this. XC, YC, CC is equal to X hat B, Y hat B, Z hat B times some 3 by 3 matrix. Let's use the letter S, S11, S12, S13, S21, S22, S23, S31, S32, S33. Okay, I have that. Okay, so let me call this matrix RAB. Okay, why do I call it RAB? So this is a description of the B frame as seen from A. Okay, so if I'm an observer, I'm standing at A, I'm looking at B. Okay, I can write the columns of the B frame, arrange the columns in this way. Okay, so this is RAB. So this is frame B as seen from A. Okay, all right, so this matrix, using the same notation. Okay, so this matrix is going to be RBC. So this is a description of frame C as seen from frame B. Okay. All right, so now we're ready to put these two things together. Okay, so what we now do is we replace this by this. Okay. So what we see is that XC, YC, CC is in fact equal to XA, YA, ZA times RAB times RBC. Okay? So it follows that this matrix here RAB times RBC is a description of frame C as seen from A coordinates. Okay, that's what this notation here implies. So this is RAC. Okay, so the final property we have is that RAC is just RAB times RBC. Okay, so if we have a description of B in A coordinates and we have a description of C in B coordinates, then we can get RAC simply as the product of RAB times RBC. Okay, so this gives you sort of a physical picture to go with the rotation matrices. Okay, we'll stop here. Of B in A coordinates, and we have a description of C in B coordinates, then we can get RAC simply as the product of RAB times RBC. Okay, so this gives you sort of a physical picture to go with the rotation matrices. Okay, we'll stop here.